Okay, hello everyone, how are you? So today we are discussing alcohol chapter. Alcohols, phenols and ethers. Just I'll revise briefly. Their first one, the preparations we know as usual. The first preparation from alkenes. I'm taking propene to explain this concept, and if it is treated with well-known reaction with a simple H plus with H2O, HgOAc twice with water in the presence of NaBH4, BH3 with THF with H2O2 OH minus. Mainly we are discussing this for addition of water. In their first one, when you add H plus ion to the alkene, now these pi electrons attract to H plus ion, then it form carbocation is intermediate. So whenever carbocation is formed, rearrangements and ring expansions are possible. Then if it is treated with H2O, water, and oxygen having lone pair, it donates electrons to the proton, positive charge, then it forms as OH group. So the final conclusion based on this reaction is, the first point, intermediate is carbocation. The second point, rearrangements and ring expansions are possible. Rearrangements and ring expansions are possible. So these two are the main important points from this part, and it follows Hoffman's rule, or it follows Markovnikov's or anti-Markovnikov's rule. We can't predict properly because whenever the rearrangement ring expansion possible, this Markovnikov's rule is not valid. Okay, so otherwise usually it follows Markovnikov's rule. But rearrangement ring expansion case, there is no Markovnikov's rule. Don't check the Markovnikov's rule. It's a very important point. I'll give you one example, you'll get idea. And next one, if I treated with mercury acetate and H2O in the presence of sodium borohydride. Now here also same, the main part, OH from H2O, H from NaBH4 finally released, and it follows strictly Markovnikov's rule. There is no exception here, and no rearrangement ring expansion. So it gives finally OH group at here and H here, because the less hydrogens containing carbon side, OH group is attacked. And next case, hydroboration with the hydrogen peroxide. Now H from BH3 and OH from H2O2. The finally addition of H2O takes place, H from BH3 and OH from H2O2, and it gives here H and here OH, because it follows anti-Markovnikov's rule, and it follows Markovnikov's rule. Finally we got alcohol from alkene with different mechanisms and conditions. So I'll show you with one more example, you'll get more clarity about this concept. For example, if they give a question like this, simple question, and if it is treated with H plus with H2O. Now see, the first pi electrons attract, will get positive charge at here, because secondary carbocation is more stable than primary, and whenever secondary carbocation is formed, see here tertiary carbon is there, so the rearrangement can possible, so this hydrogen can migrate, and it gives here positive charge, and this hydrogen shifted here. That means, see here, the secondary carbocation becomes tertiary, so the tertiary carbocation is more stable, hence the reaction takes, the migration easily takes place. And finally we have to add water. By adding water, it gives OH group at here. That means according to Markovnikov's rule, OH group at second carbon, but here there is no Markovnikov's rule because of rearrangement ring expansion cases. So here in this case, rearrangement. So whenever rearrangement ring expansion takes place in the given molecule, chances are there, then there is no Markovnikov's rule. You have to go according to stability of carbocation. Okay, and if I go for second one, mercury acetate with D2O, that is assume, and NaBH4. I said it follows Marconi-Cauchy rule. So the compound same, and here OH, here H. But I said OH from H2O. OH from H2O. So here H2O plus what? D2O is there. That means what we will get? OD. And H from NaBH4. What is the H here? H only as it is, because they gave NaBD, NaBH4, not BD4. BD4 means you will get differently. Okay. Now here D2O is there, OD. So OD attached at here and H at here, because OH from H2O, but here OH plus OD is there, and H from NaBH4 as usual, and it follows Marconi-Cauchy rule. And the same reaction if I go with BD3 with H2O2 with OH minus, BD3 with H2O2 with OH minus. In this case, see, it follows anti-Marconi-Cauchy rule, and H from here, but H plus here D is there, and OH plus same as H2O from OH, H2O2, OH from H2O2, and here OH is as usual, and it follows anti-Marconi-Cauchy rule. So here H, here OH. So H plus here D, OH plus as usual OH, because it follows anti-Marconi-Cauchy rule and the source. So this kind of isotopic reactions also important for our exam. And the next one, if I take this reaction also we discussed in hydrocarbons, propene. If I take propene, if it is treated with H2SO4 with HgSO4, or else sometimes they'll give H plus Hg plus 2, both are same. The entire this reagent, whenever they give H2SO4 and HgSO4, it's important, and we need to know, or we consider as addition of water. H2O is addition, and it follows only Marconi-Cauchy rule. Rearrangement ring expansions are not possible. Direct Marconi-Cauchy rule, like mercury is the direct Marconi-Cauchy rule. Here it follows Marconi-Cauchy rule, and here also Marconi-Cauchy rule. This is for alkene, this is for alkyne. Now what happens, see, in this case here one hydrogen is there because of CH, and here no hydrogen, zero hydrogen. So according to Marconi-Cauchy rule, the OH group negative part attached on less number of hydrogens containing carbon. That means here double bond as usual, and we'll get here OH and here H, just addition of water. Now whenever water is added, see, it's looking like enol form. It is involved in tautomerism like this, and it form as ketone. Okay, so finally we will get here ketone. There is no alcohol formation here, so by addition of water we won't get alcohol. Enol is get, but enol is not stable, again it convert into keto form. The next, I'll explain in this one the main important reactions, like the preparations only. The preparation from alkyl halide, it's okay, very simple reaction, just I'll write one time. We'll get it, it's very easy. Just we can take primary alkyl halide or secondary alkyl halide or tertiary alkyl halide. It is react with DMSO. DMSO is nothing but CH3S double bond O, CH3, dimethyl sulfoxide or sulfonyl oxide, so DMSO. Now if I used this reagent, the name of this reaction is called Korn-Bloom oxidation. Korn-Bloom oxidation. Now here simple, here H is there, so two hydrogens are there. So whenever this oxygen is inserted, this HCl is removed like this. This HCl removed and oxygen is inserted here instead of HCl. The shortcut just simple oxidation. Simply we can write like, finally here oxidation, I mean oxygen is there and hydrogen also, C double bond OH, that is aldehyde. Now here also H is there and here oxygen, that oxygen is inserted here, then you will get ketone, and here no hydrogen, that means no reaction, because we need at least one alpha hydrogen, but here alpha hydrogen is there, here also there, but here no alpha hydrogen, hence no oxidation. So by using DMSO, primary alkyl halide give aldehyde, secondary alkyl halide gives ketones, but this one no reaction. See, we got here aldehyde and ketone, and by reduction we will get here primary alcohol, and here by reduction we will get secondary alcohol. That part also we need to know. Okay, so now I'll give you preparation of alkyl halide from carbonyl compound by using all reducing agents. So this one is important. This is important. Reactions like reduction. By using reduction, all carbonyl groups converted into alcohols. See, I'll show you. If I take just a minute. See, the first reaction I'm taking acid halides RCOCl. If acid halide involved in reduction, the reduction is nothing but, we know, this double bond cleavage and keep hydrogens on both sides, and what will get the answer? C, RCOH, here H and Cl, right? So this is simple reduction. By using any reducing agents we can take. Let us assume I'll give you some reducing agents like LiAlH4, NaBH4, B2H6 with H plus, sodium with ethyl alcohol, H2 with nickel or platinum or palladium, any of these. The mainly we are using here 4 reagents I took here. So now see, now whenever this carbon having OH group and Cl, this carbon having 2 electronegative atoms, so immediately this bond shift and this one also shift. Then what will get the answer? C, it gives RC double bond OH, right? So H and Cl removed, it become aldehyde. This aldehyde again involved in reduction will get hydrogen hydrogen, and finally it gives RCH2OH, and finally we got primary alcohol from acid halide by using reducing agents. So which reducing agents are mainly suitable, I'll tell you. Second one, if I take aldehyde, we know here the cleavage takes place, this bond cleavage, and we'll get 2 hydrogen atoms because of reduction. I'll tell you clearly what happened reduction exactly here. RCH2OH, okay, this hydrogen at here and this hydrogen at here, so we'll get finally RCH2OH. That means we got primary alcohol from aldehyde. If I used third one, RC double bond OR, ketones, the ketones under reduction it gives RCOH HR. That means we got secondary alcohols, and this is the cleavage, keep hydrogens on both sides, reduction. And next one, acid anhydride. This acid anhydride, see, this will undergo reduction. For example, HH, we will get RCOH and here HOCOR. And again see, we know this is the best living group according to nucleophility or living capacity. So we need to know in GOC already we discussed, or check once, living capacity, or SN1 SN2 reactivity time also we discussed, living capacity or nucleophility. So based on that, when the carbon having 2 OH groups, this group removed and here hydrogen also removed, and finally we will get RCOH. We'll get aldehyde because RCOOH removed and it gives RCOH aldehyde. This aldehyde again involved in reduction, it gives RCH2OH, RCH2OH, and finally we will get alcohol. Finally we will get alcohol. So the next part, see here alcohol is formed. Now the fifth one, RCOOH, carboxylic acid I took here. The next one, carboxylic acid. Now here this group involved in reduction, it gives RCOH HOH. So now Okay, so now this carbon having two OH groups, again same H2O removed, and it gives aldehyde. Okay, so this aldehyde gives again alcohol, same as previous concept. So this part is same. And if I go for sixth one, RCOOR, ester. If it is involved in reduction, it gives RCOHOR, and here hydrogen is there. When the carbon having two oxygens, so immediately this bond shift, like alcohol is removed, minus ROH, alcohol removed, will get aldehyde. This aldehyde again gives alcohol. So what I am discussing here, finally all carbonyl compound gives alcohols by using reducing agents, but few compounds required 1 mole, few are required 2 moles, sometimes more. So now seventh one, or carboxylic acid, ester. The seventh one is amide. This amide case is important whenever it is involved in reduction. So keep two hydrogens on both sides, RCOH, H, NH2. We got carbon with OH and NH2 group, and this point is very important. See here, this point important. Now whenever this carbon having OH group and NH2 group, OH CO bond is weaker than CN bond because of polarity. The oxygen is more electronegative than nitrogen. So CO bond having more polarity than CN. That means more polarity means this bond can easily break, not CN. So this OH group removed, that means CO bond cleavage, not CN. COH bond removed and H also simultaneously removed, and it gives RCH double bond NH2. We will get imines. This is called imine. Amine gives imines. This imines involved in reduction, both hydrogens will get RCH2 NH2. We will get finally amines here. So amide gives amines. The remaining all gives alcohols. The remaining all carbonyl groups gives alcohol. And the next one here, see, the first case, alkyl halide gives alcohol. So this alkyl halide gives alcohol by LiLH4. Lithium aluminum hydride can reduce, or sodium borohydride can reduce. B2H6 cannot reduce, and sodium ethyl alcohol reduce, or H2 with a nickel reduce. Why can't with B2H6 with H plus here? The reason is, see, the B2H6 is electron deficient. That means it has vacant orbital. Only here 12 electrons are present. 1, 2, 3, 4, 5, 6, 12. See, because the diborane structure, we know the 4 terminal hydrogens and 2 are bridged hydrogens. So it has 2 electrons, 3 centered bond. So the B2H6 having only 12 electrons instead of 16. So it's electron deficient. So whenever the atom is electron deficient, and it acts as reducing agent, because LiLH4 release H minus, NaBH4 release H minus, and BH3 also release H minus, and here H plus removed from here and direct addition of H2. These are the source of hydrogens from these reagents. So here H minus and here also H minus, and here H minus is difficult to lose because electron deficient compounds are present. First it required some electrons to lose this H minus. So if I used aldehyde having lone pair here, and here also lone pair, but here also lone pair is there, but chlorine is the electron withdrawing group. So whenever electron withdrawing groups are there, electron withdrawing group containing compounds cannot reduced by B2H6. So not only acid halide, because acid halide having electron withdrawing group, not only acid halide, we can take NO2, cyanide. All these groups are strong electron withdrawing groups. They can't reduced by B2H6. They cannot be reduced by B2H6. And if I go for second part, aldehydes, yes, aldehydes can reduced by all compounds. There is no exception. For ketones also same, they can reduce all. acid anhydride, yes, by LiLH4, but not with sodium borohydride. The reason is LiLH4 and NaBH4, the strongest reducing agent is LiLH4 and mild reducing agent is sodium borohydride, because here more ionic character is more, aluminum hydrogen having more ionic character. Whenever the ionic character is more, H minus easily removed from here, because aluminum can exist as +3, but boron can't exist as +3 because it's a covalent and it is ionic. So ionic compounds can, ionic character it can show, so it can lose H minus, but here difficult to lose H minus. That's why LiAlH4 is the strongest reducing agent and NaBH4 is mild reducing agent. So LiLH4 can reduce ester, because see this carbon having partially positive, whenever the H minus approached here, in this case there is no donating group, but here oxygen having lone pair or not, whenever oxygen having lone pair, they donates electrons, so this charge decreases. Whenever the charge decreases here, H minus difficult attack at here. So simply what I want to tell you, the point is, if donating group is there, any donating group, see here also donating groups are there, NaBH4 can't reduce. Normal groups it can reduce, but here plus I group not affected much, but here plus M groups are there, so they are more effect on carbonyl groups, so H minus difficult attack on here. That's why there is no reaction. But here one exception is there for NaBH4, that is cyclic anhydrides. Cyclic anhydrides can reduced by NaBH4, just keep in your mind, only cyclic anhydrides can reduce, and B2H6 can reduce, and sodium with ethyl alcohol can reduce, and H2 with nickel can reduce this compound to alcohol. And carboxylic acid, yes, LiLH4 can reduce, but NaBH4 no, ester yes, and here no, amide yes, but here no, because I said these all are electron donating groups. And B2H6 can reduce 5, 6, 7 all compounds, but sodium with ethyl alcohol can't reduce carboxylic acid, rest part okay, because sodium metal, whenever the sodium metal is there, the sodium reacts with the carboxylic acid. Here acidic hydrogen is there or not, so acid base reaction takes place. Instead of reaction at carbon, reaction at hydrogen takes place with the sodium metal. So usually the metals are there, usually there is no reduction of carboxylic acid. That's why here also no reduction with the H2 nickel, also no reduction. Exception, keep in your mind, ester cannot reduced by H2 with nickel, amides can reduce. So the exceptions for H2 with nickel is as carboxylic acid and amide. For sodium ethyl alcohol, carboxylic acid. For B2H6, acid halide, NO2 group, cyanide. For for NaBH4, rest all are except only these three: acid halide, aldehyde, ketone. The remaining all are cannot reduced by this reagent. Okay, so this part is more important. Okay, now we'll continue in the preparation only in their the next part. I'll give you some examples based on the reduction, then we'll go to the next part. In their first one, examples for reduction table, earlier table. And there, if I take acid anhydride with some CH3 group I took here, that's also useful 100%. First reaction with LiAlH4, I'll tell you. We know LiAlH4 release H minus hydride ion. Now this carbon is partially positive and here also partially positive charge. But see, whenever donating groups are there, here methyl or ethyl, whatever any or OH group, some electron plus M effect, here plus groups are not affect, plus M not affecting, only plus I groups are present. They are donating groups. Whenever donating group is there, see, the here charge decreases, but here donating group also with this group, but it's a far, see 1 2 3 third position, from here second position. I said inductive effect is a distance factor. Whenever the group is far, the effect is less. So here effect is less, here effect is more. Which effect is more here? It decreases H minus, because whenever it donates electrons, the charge decreases, H minus difficult attack on here. So what I want to tell you, the point is here, nucleophilic addition, important, very very important. Nucleophilic addition is directly proportional to electron withdrawing groups and inversely proportional to electron donating groups. So donating groups are there, nucleophilic addition is difficult, and withdrawing groups are there, nucleophilic addition easy. So now here donating group is there, so nucleophilic addition is difficult. So now see how to write this compound. I'll tell you. First here reduction takes place at here, so this bond shift, we will get hydrogens on both sides. So I am writing this compound as usual, as it is, OH, O, double bond O, CH3, and here hydrogen is there, no need to write, we know it. When the carbon having two oxygens, see both are having repulsions. When the carbon having two oxygens, so this bond easily cleavage because 5-membered ring, and this group is difficult to remove, the cleavage takes place. And why here the cleavage takes place? After formation of O minus, it is involved in resonance with this oxygen, so this bond can easily cleavage instead of this one. See, if it is removed, only OH minus is formed, but if this bond cleavage, the negative charge involved in resonance, so this bond easily break. Then how it exists, see, we'll get here double bond O, and hydrogen is there, hydrogen is there, and here C double bond O, O minus methyl. And we know just here water, obviously H2O will be there, otherwise you can't get O minus to H plus, OH alcohols. So we'll get OH at here, H at here, so we'll get C double bond OH. That's it. So now see, I'll show you. Okay, now we got one side aldehyde, one side carboxylic acid. But if I take excess of LiAlH4, see, aldehydes also can reduce or not. Aldehydes reduce to alcohol, and carboxylic acid also reduced to alcohol. Earlier table, just check it, you will get idea. Now what is the answer? See, here OH group, here methyl as usual, and here also OH. So finally we got 1 2 3 4, 1 2 3 4, first and fourth carbon having OH groups, the remaining all are as it is. Okay, so we got this compound. But if the same reaction, this one I am taking again, the same reaction with NaBH4. See, generally cyclic anhydrates can reduce by NaBH4, but normal anhydrates can't, but cyclic anhydrates can reduce. So till here as usual, first reduction, everything is same. We'll get aldehyde and carboxylic acid, methyl. But again, if I used excess NaBH4, here the case, we know aldehydes can reduce to alcohols, but carboxylic acids cannot reduce. Carboxylic acids can't reduce by NaBH4. That means what we can write here, C OH, but here COOH, and here methyl. That means, see the difference between these two. Here OH group as usual, but here all carboxylic acid converted into alcohol, but here carboxylic acid as usual, because carboxylic acid can't reduced by NaBH4. So this way we can predict reactions. So this part is very important, what I earlier explained table, so you can practice more questions based on this part. So now we are discussing some physical properties of alcohols. These are the preparations till now what we discussed. Now the physical properties. The first physical property we know, acidity. The acidity part is very important, so I'll explain. If I used methanol, ethanol, propanol, tertiary butanol. Okay. Now out of this four, which is more acidic? Only one factor we need to know, that is acidity always directly proportional to electron withdrawing groups and inversely proportional to electron donating groups. So this part we discussed more in GOC part, so you will get idea there, factors affecting on acidity. There we will discuss acidity always directly proportional to electron withdrawing group and inversely proportional to electron donating group. So what are the electron withdrawing groups here? Which groups are present here? Methyl, here ethyl, here isopropyl, here tertiary butyl. All are alcohols, but see here 1 carbon, here 2, here 3, here 4. Where more plus I groups are there? Here more plus I groups. So plus I group means donating group. Donating groups are more, SDD less. So what we can write here, the answer is 1 is greater than, 2 greater than, 3 greater than 4. Answer is methanol is more acidic than ethanol, isopropyl, then tertiary butyl alcohol. And the solubility we have to see, which is more soluble. This is also important. The solubility is directly proportional to, the first point is directly proportional to branching we have to see, and inversely proportional to chain length. And before that we have to see number of carbons also. It must be same. So this part is very important. Just I will show you here. See. The solubility is directly proportional to number of carbons, directly proportional to branch, inversely proportional to chain length. I'll show you with example. See, I'll show you. See, for example, OH, like this, okay. With this they give compound like this. Now here only 2 carbons are there. Here 1 2 3 4 5 carbons, 1 2 3 4 5 carbons. Here also 4 5 carbons, okay. So now the chain length, the branch is nothing but chain, surface area we have to see, okay. So now the 2 carbons only, so it has more, so earlier number of carbons inversely proportional, solubility inversely proportional to, I'll show you earlier. This part, inversely proportional to number of carbons, directly proportional to branching, and inversely proportional to chain length. Because number of carbons are more. Carbon is nothing but what? Polar or non-polar solvent? It's a carbon is non-polar compound. Non-polar compounds are insoluble in water. So more carbons are there. What happened? Insolubility increases. But alcohol group is there. So usually organic compounds cannot soluble in water, but alcohol can soluble. We know very well. Alcohol easily soluble in water, but due to hydrogen bonding, but number of carbons are more. Usually it's a number of carbons more than 6 carbon atoms. So those alcohols, that means hexanol onwards, those alcohols insoluble in water because of organic compound is more. That means non-polar character is more, polar character is less, they are insoluble. Now in this case the question is only here 2 carbons, here 5 5 5, so 100% it can easily soluble. The first one is more soluble, okay. After that, here chain length is more, here chain length is less. I said branching is required more. So more branches where? Here more branches. So answer is 4 3 2. So first we have to check number of carbons, then go for less surface area, more soluble. We know, based on that we'll get idea, okay. So this is the answer for the solubility. So this way they can ask question like solubility and boiling point, melting point. Mainly we are discussing the boiling, melting point mainly depends upon the first factor is molecular weight. If molecular weight is same, go for hydrogen bonding. So based on hydrogen bonding and surface area, based those factors we will get. Now we'll go to chemical properties, okay. In their chemical properties, the mainly we are discussing cleavage of OH group. See, if it is alcohol, the alcohol mainly cleavage 2 types. This is the first cleavage, second cleavage. So maybe CO bond can cleavage or OH bond cleavage. We'll discuss one by one, you will get more clarity. If I take this cleavage example, we'll discuss. If I take like alcohol, and if it is react with concentrated H2SO4, we know concentrated H2SO4 acts as dehydrating agent. That means it removed water from the compound through E1 mechanism. We know E1 mechanism already we discussed in alkenes chapter, and also alkenes chapter we discussed halogenation, dehalogenation and all. So this is under dehydration. So now the H and OH removed like this and we'll get alkene, right? So now finally which cleavage takes place? RO cleavage takes place from here. And one more important here, that is esterification. Esterification will get as OH cleavage, that is under OH cleavage. We'll discuss under OH cleavage, not CO cleavage. That's it. The mainly only this reaction is important for the cleavage of CO, and we'll discuss second one, ROH cleavage. Esterification we'll discuss here. Now esterification important. See, if I take carboxylic acid treated with alcohol in the presence of H plus ion, acidic medium. Now the case is here, the OH either removed from here or maybe from here. That is very important, because the final answer is what? H2O removed, and it gives RCOO R dash plus H2O. This H2O removed from this OH and here H, or here OH and here H, we need to know. Generally what we are expecting is acid, acid means it loses H plus ion, here OH, so it forms as H2O. That is wrong. OH removed from carboxylic acid, H removed from alcohol. This is important. Okay, the cleavage H from alcohol, OH from carboxylic acid, and finally we got ester. So here which cleavage takes place? OH bond cleavage. Now that's why under this one I discussed. Now see what happened exactly. Mechanism we need to know. First, if I take with carboxylic acid, why I took carboxylic acid also I'll explain. See, here oxygen having lone pair, it is involved in resonance, but here oxygen having lone pair, no resonance. So this is a strong base center, so it donates electrons to the proton, and it forms as RC double bond OH, and here plus, and here OH. Okay. Now this carbon having double bond, whenever the carbon having double bond, see this bond shift here, like because O plus is highly unstable, it gives RC OH OH, and here plus RCOOH plus. That's why I took first carboxylic acid, because this carbocation is more stable with resonance. But if this oxygen is involved, for example alcohol oxygen is involved here, this is unstable, so it's not, this can possible but not preferable product. The major product is what I am taking is major product. The rest all are possible products. It's not a matter for you. So now this carbon having positive charge here, stable intermediate, then we can take alcohol, oxygen having lone pair, it donates electrons to this compound and it gives RCOH. I am taking another OH here, and this part O R dash, because simultaneously here H plus I removed. Now this carbon having two OH groups, immediately H2O removed, RC double bond O R dash. So where OH and H removed, how to predict? Very simple. See, I took for example this one is O18. Okay, so which is O18 here? This is O18 and this is O18 and this is O18. That means O18 is where? In the ester, and H2O no O18. The meaning is what here? O18 in the ester, H and OH removed from this part. So by using isotopic elements we can find out mechanism steps. Okay, so the finally we got ester from carboxylic acid and alcohol in esterification. This is called Fischer's esterification. And if I use the same reaction with RCOCl now, so instead of OH I am taking chlorine. Now instead of H2O we will get HCl. That is called Fischer's acylation. So acylation also same. We can take here acid halide or acid anhydride or carboxylic acid. All gives esters only. So these reactions are called Fischer's acylation. So now in this case, the main important point is in this esterification reactivity orders. The reactivity order of carboxylic acid. See, if I take methanol, ethanoic acid, propanoic acid, isopropyl, tertiary butyl groups. If I took like this, now out of this four, which one having more involved in esterification means 100%. First one, less crowded, because its esterification is inversely proportional to steric hindrance. Because see, this whenever this group is found, another group is coupling. See, more crowded groups are attacking here, right? So whenever this group approaching here, these two alkyl groups must be small. If it is any one is large, then the repulsions are more, the bond formation is difficult. That's why here rate is completely depends upon steric hindrance. Less steric hindrance, more esterification. The same thing for alcohols also. Methanol, ethanol, isopropyl, tertiary butyl alcohols. Here also same. The methanol is more react because less crowded. So we have to check where less crowded combination, there esterification easily takes place. Okay. And now we are discussing here one more, that is oxidation part. Just briefly I'll explain oxidation. Just I am revising complete chapter, so practice, you can practice questions, and any doubts you can ask me. If I take primary alcohol, secondary alcohol, tertiary alcohol, okay. If I used mild oxidizing agent, what's the meaning of mild oxidizing agent? The meaning is it lose only one nascent oxygen. If it is a strong oxidizing agents means they give excess or 2, 3, 4. Minimum 2 is enough for us. So 2 nascent oxygens gives, that is strong. 1 nascent oxygen, that is mild. Okay. So now if I used primary alcohol, see this carbon is alpha, right? Here hydrogen is there. Here also hydrogen is there. So whenever the alpha hydrogen is there, so this oxygen easily inserted here and it form as OH. Whenever the carbon having two OH groups, immediately H2O removed. And what is the final answer? C, H3, C double bond O, H. We will get aldehyde. But if I used two nascent hydrogens, first we will get aldehyde like previous one by using first nascent oxygen. If I used a second, see this is aldehyde groups are easily involved in oxidation and they form as carboxylic acid. Understand? So first one gives aldehyde, second one gives carboxylic acid. And this one either we can use mild or strong, it's not a matter, because OH group and here H is there, H plus I can take OH because oxygen inserted at alpha. Oxidation always takes place at alpha, that's acidic hydrogen. So whenever the carbon having two OH groups, here H2 are removed and it gives ketones. See, there is no another oxygen required here. Yeah, okay, there is no oxygen required here because ketones never involved in oxidation. Okay, primary alcohol gives aldehydes, carboxylic acid, secondary alcohol gives only ketones, and by using tertiary there is no alpha hydrogen and all oxidation. Aldehydes, carboxylic acid, secondary gives ketone, tertiary no reaction. And what are the mild and strong reagent? Just I'll give you some idea, and more you can read from your books. Okay, so the first one, MnO2 with CH2Cl2. What the use of this manganese dioxide means? It can oxidize allylic and benzylic alcohols. Okay, allylic and benzylic alcohols convert into aldehyde. The rest cases there is no reaction. The second mild oxidizing agent, K2Cr2O7 H plus with cold. And third one, very important, PCC, pyridinium, like this, pyridinium chlorochromate. Pyridinium chlorochromate. So whenever they give CrO3, usually it is pyridinium chlorochromate, then it is mild oxidizing agent. The fourth one is DMSO, dimethyl sulfoxide. Earlier Korn-Bloom oxidation also explained, there I gave. Fifth one, Fenton's reagent. This is usually used in carbohydrate chapter. It acts as mild oxidizing agent. FeSO4 plus H2O2. Rough degradation we are using Fenton's reagent, that is FeSO4 plus H2O2. And the sixth one is CAN. This is used for test for alcohol groups, OH group. Wherever the OH group is there, it gives CAN, ceric ammonium nitrate. Ceric ammonium nitrate. These all are acts as mild oxidizing agents like earlier case. And seventh one, PDC in CH2Cl2. PDC is nothing but pyridinium dichromate, Cr2O7. Like K2Cr2O7, the K plus place pyridinium is there, that is called PDC. K2Cr2O7, same like K2Cr2O7, but K place pyridinium, then it is called PDC. So the PDC acts as mild oxidizing agent in CH2Cl2. And strong oxidizing agents, and here one more, that is copper or silver at 300 degrees. That is also mild oxidizing agent. And strong oxidizing agents well known, that is KMnO4 with H plus ion or base OH minus. The second one is K2Cr2O7 with H plus hot conditions. And third one is, as just now I said, PDC but in DMF, dimethyl formamide. This is dimethyl formamide. Two methyl groups with the formamide. Dimethyl formamide is the solvent. By using this solvent, we will get it acts as PDC acts as strong. And fourth one is Jones reagent. Jones reagent is nothing but H2CrO4 plus H2SO4. If I used H2SO4, H2CrO4 plus H2SO4 acts as a strong H2CrO4 plus acetone, then it acts as mild. So this is mild and this is strong. So whenever they give H2SO4, we have to check strong. So that is the difference, very important. Jones reagent, either they gave one more CrO3, sometimes they'll give with heat, then also it acts as strong. So it's very important to identify. So better refer few books. Now also not a problem, you have a lot of time. So now just go through it, all the mild and the strong oxidizing agents based on Google source, or maybe you can check with standard books. Better go with some standard books like organic standard books like Wade is there, Claydon, sorry, not Clemenson. Clemenson is a reduction. Okay, the Claydon is there, or go with Moisen Bide, Jerry March not for you, Brewis or Moisen Bide. You can search in Google, you will get idea, so many books, so check from there. So these all are acts as mild and strong oxidizing agents and in nature. So these all are very important. So better you can search in your book and practice more questions, very very important. So now I'll give you one or two examples here just for practice, but not depth here. Simply I'll tell you just for I took this compound. If it is treated with manganese dioxide with the dichloromethane, okay, see it acts as mild oxidizing agent at primary and secondary at allylic and benzylic carbon. See, double bond next carbon. This is allylic. This is allylic, double bond. This is double bond next carbon, but this is not allylic carbon. So only this alcohol reduced. Sorry, alcohol oxidized to aldehyde because of mild, and these two are not affected. The next one, if I used PDC. The PDC is the mild oxidizing agent. It can oxidize all primary and secondary alcohols, any alcohol. So here double bond as usual, and it gives alcohol to aldehyde, but it's a tertiary alcohol can't oxidize, and the secondary alcohol cannot into ketone. This is primary, this is secondary, it's a tertiary. And if I used PDC, it's not good for because of unsaturated bond is there. H2CrO4 plus H2SO4 I am using. Now see, it acts as strong oxidizing agent, so it can oxidize secondary alcohol to ketone, tertiary alcohol no reaction, but primary alcohol gives carboxylic acid, this double bond as usual. So this is the compound, right? The last one I'll tell you, it is copper or silver at 300 degrees. The best one is silver, then copper. Silver is the best oxidizing agent. So now by using this reagent, it oxidizes mild oxidizing agent, so it oxidizes primary alcohol to aldehyde, no doubt, secondary alcohol to ketone, and tertiary alcohol to alkene, because at 300 degrees elimination takes place. So either left side hydrogen or maybe right side hydrogen, any one can remove. But see, from the left side we'll get double bonded here, from right side here, and this double bond is more stable with the conjugation as well as more branches, and this is unstable. So 100% we will get more stable alkene formed at tertiary. Okay, primary gives aldehyde, secondary gives ketone, and tertiary gives alkene. And next part, just a minute. Okay, the next part we are discussing distinguished test. We know Lucas test. I'm not discussing here. We know already that part. The Lucas reagent is concentrated HCl, anhydrous ZnCl2. Concentrated HCl, anhydrous ZnCl2. Primary alcohols gives white turbidity after warming. Secondary gives after 5 minutes. Tertiary gives immediately this test, because SN1 reactivity order we know tertiary is more reactive than secondary than primary. Hence SN1 according to SN1 reactivity, tertiary is more reactive. Hence primary alcohol, tertiary alcohol immediately gives turbidity with this reagent. Then secondary 5 minutes, and primary takes after warming. Okay, after warm heating. And the next one, Victor Meyer test. This is important. I'll explain this test. This is also we are using for test for primary, secondary and tertiary alcohols we can distinguish. In the first one, if I used primary alcohol, at a time I am taking all three. Secondary alcohol, and tertiary. The first reagent is HI, or iodine I want to substitute. So instead of that I can take I2 with phosphorus, because I2 with phosphorus gives PI3. PI3 react with alcohol, it gives iodide. Okay, here also same iodide, here also same iodide. Substitution I took it. Then if it is treated with AgNO2, AgI removed as precipitate and it forms as NO2, NO2, NO2. Till here same, right? The next one, treated with nitrous acid. See here, alpha hydrogens are 2, so these 2 alpha hydrogens and this oxygen removed as H2O, and it forms as, here NO2 group is there, then double bond NOH. See this group I attached it here, and this carbon and nitrogen having double bond, because here 2 hydrogens lost, instead of that 2 double bonds are forming here. Okay, and in this case only one acidic hydrogen is there, so this H and OH removed and it forms as NO2 N double bond O. But here no acidic hydrogen alpha carbon, hence no reaction. Clear? And I am using one more reagent to distinguish first and second. So sodium hydroxide. Whenever we used sodium hydroxide, see here acidic hydrogen is there or not? OH group is acidic group, right? So this H plus and base react and it forms O minus Na plus. This is actually red colored precipitate, and if it is treated with NaOH, here no acidic hydrogen, hence no reaction with this, but this is blue color compound, and here no reaction, so usually this is colorless white. So if we know if the given one is primary or secondary or tertiary, we can easily identify. If it is primary, it gives red, secondary blue, tertiary white. So that's why it is called, another name, Victor May test, RBW test, red blue white test. Right? Now we are discussing diols. Diols. In their first part, usually the preparations are easy. We can take alkenes. The alkenes reacts with Bayer's reagent, cold dilute alkaline KMNO4, OSO4, or MCPBA with water. Any of this all gives 1,2 diols, 2 OH groups on 1,2 side, right? So but Bayer's and OSO4 use syn addition, that means 2 OH groups are same side. MCPBA use opposite, we know well known that part. And this reaction is important. If I used ketone in the presence of, this is the hint, they'll give magnesium amalgam with ethanol. It's a solvent. So what is the use of this reagent? See, whenever these ketones they give, they first involved in homolytic fission and reduction takes place. This H group attack it here, and homolytic fission takes place, we'll get the free radical. Understand? And I'm using, see, this H from here, ethanol hydrogen H plus is there, now that H plus attack it here and it forms as free radical. And I'm using the same compound, one more, Now whenever the free radicals are there, we know like Woods reaction and all, coupling takes place. Here also coupling takes place, and it gives like this. So these two free radicals are coupled and we got like this. This is called pinacol. What is pinacol? Tertiary 1,2 diols are called pinacols. We know pinacol, pinacalone rearrangement. Now we are discussing that part, don't worry. Pinacol, pinacalone rearrangement also we will discuss now. Now these two are the main preparations of diols. Now we'll go to chemical properties. In there, first one, just now I said pinacol, pinacalone rearrangement. What is pinacol, pinacalone rearrangement? See, I am taking pinacol first, that is tertiary 1,2 diol. Just a minute. This is pinacol, okay, tertiary 1,2 diol. If it is treated with H plus ion and finally it gives pinacalone like this. This is pinacol, this is pinacalone. This rearrangement is called pinacol, pinacalone rearrangement. What is this rearrangement? I'll tell you now. See the mechanism. First I am adding H plus ion to this pinacol. Here oxygen having lone pair, here also lone pair. Any one of the OH group can attack. We will get OH group here and plus charge. In this molecule there is no problem because this molecule is identical carbons, right? For example, here some phenol group is there and here methyl groups. So now in these two, where OH removed easily? 100% carbocation stability we have to check. So if hydrogen OH removed from here, positive charge formed, but this is more stable with resonance of benzene, and here positive charge formed only methyl groups. Methyl groups means only hyperconjugation takes place. Here resonance, here hyperconjugation, which is more preferable resonance. Hence this OH is removed. So we have to check which OH group easily removed. How to check it? Based on the coming carbocation. Which carbocation is more stable, that is that group easily removed OH. Okay, now you will get idea with example. For example, here phenol is there. Now I can remove this OH or this one, but I am removing only, you will get later, we will discuss. Okay, both are identical, I removed, normal. Now tertiary carbocation, whenever the tertiary carbocation is there, see here carbocation is formed, rearrangement, ring expansions are possible. This methyl group migrate, and we need to know the migration tendency order. The first one is hydrogen, then phenol, then electron donating groups, electron withdrawing groups. This is fixed for all, almost. Exceptions are very few. So hydrogen, phenyl, electron donating group and electron withdrawing group is the least preference. Now see here methyl groups, two are methyl, not a problem, any one migrate. Whenever the group migrate, this group migrated here, I am writing methyl group, another methyl is there here, OH, and this methyl group removed as negative charge, so we will get positive. Usually here tertiary carbocation and here secondary, which is more stable? Tertiary is more stable, right? But in this case secondary is more stable. Why secondary is more stable here? See, oxygen having lone pair or not? Resonance. Resonance is more stable than hyperconjugation now. So hence this carbocation is most stable with resonance, so migration can possible in this case. And the final answer is this one you will get because of shifting of proton. The proton is a removed proton from here, and we'll get double bond, and finally we got penacalone. I'll explain two examples. You'll get more clarity about this concept. First example I'll give you, tell me answering only. Answer for this question. Try yourself, and one more I'll give you. These two questions. Okay, so I'll tell you now. See the answer for the first one. Here phenyl group and here ethyl group is there, so this carbocation is more stable, pH due to resonance. And here ethyl group, methyl group and OH. Now we know methyl ethyl, which is more donating group, ethyl group migrate because more donating group is ethyl. Positive charge, then again this bond shift, we'll get final answer is like this. Okay, if you got like this answer, then you are good. The next case, the H plus, here NO2 group I took here, so whenever NO2 group is there, withdrawing group decreases carbocation stability, so the positive charge must be formed at here. Okay, see, question important. Highly specific here, so this OH is as usual and we will get positive charge at here, correct? So whenever the positive charge formed here, we know rearrangement or ring expansion. In this case 5-member ring, next positive charge, ring expansion possible. So in this ring expansion, very careful, either this bond can migrate or this one, either this one or this expansion, which is correct 100%. In this case below 1 correct, above 1 is wrong. The reason, this group is close to this carbon or not. Whenever the withdrawing group is present, I said migration tendency order, electron withdrawing group tendency is least, right? So this group is close to this carbon, so this shifting is not possible, and here ring expansion can easily possible. So 100% reaction takes place through this one. I'm giving the numbering 1, this is 2, this one expanding now, 3, 4, 5, 6, 1, 6, new bond. This bond expand like this, 1, 6. How? I'll show you. See here. Like this. Why I'm writing like this? See, this is the first carbon as usual. Now this is second, third, fourth, fifth, sixth. The new bond between 1, 6, right? 1, 6 new bond. And 2, 6 lost the bond. Okay, 2, 6 become 1, 6. Now where will get the positive charge? On second, and NO2 group is at 4th position. and OH group at second carbon, right? OH group is at second carbon only, na? So be careful with the numbering, then 100% easy these questions. So little bit complicated, but by practice, nothing. H removed and this bond shift, and the final answer is this is the answer, no doubt at all. Okay, so first, which group is removed and ring expansion, so those two we need to know. So this part I want to tell you from this alcohol chapter, and we'll go to ethers. In there, first one, preparation, important one only I'm discussing. Williamson synthesis I'm not discussing, you know already. I'm taking HgOAc twice with alcohol, sodium borohydride. Earlier I explained this one saying the preparation of alcohol, but there I took H2O, but now I took here alcohol. H2O lose OH minus, and this one dissociated as RO minus H plus. That means what? It lose RO minus and it lose H plus, and it follows Marconi causal, same as previous H from NaBH4, OH from water. Instead of OH, now I took here ROH. That means instead of water I took here ROH. So there OH removed, here OR removed. Okay, that means OR attack and here hydrogen attack on this alkene, and it follows Marconi causal. How it will get? See, OR, here H, addition of alcohol now, because I took here alcohol, na? Earlier I took water means addition of water, alcohol addition of water. So now in this case finally we got ROR is nothing but ether. Okay, and Williamson synthesis already we discussed earlier, last section only, so just go through it, you will get idea. The main preparations of ether, this one, and a few more are there, you can study from your NCERT textbook. Then the most important concept from this chapter, maybe 2020 NEET we can expect this question, chances are more, that is reaction with HI. What is this reaction with HIC? The first one I'm taking, one side tertiary alcohol, tertiary alkyl group, other side ethyl. HI, will tell you what I am discussing. One side ethyl, other side propyl, maybe methyl. HI. Third one side phenyl, other side any alkyl group, it's not a matter. HI with cold condition, I'll tell you what's the meaning, I'll tell you now. See, this one is cold and this is hot, this is cold and this is hot conditions. That means at high temperature, low temperatures. Here the case. So if they give questions, how to solve it? See, here two kinds of cleavages can possible. See, this bond can cleavage, then what happened? Oxygen side H and I. In HI, H is positive, I is negative, right? So O side H will attack and here I can come. That means what is the answer finally? Tertiary butyl iodide propanol, right? If this bond cleavage, then what happened? Here H, here I. Then what is the answer? Ethyl iodide tertiary butyl alcohol. Earlier is what? Ethyl alcohol. Now here tertiary butyl alcohols are forming. That means two different products we are getting. So now in this two, which is correct? 100% this one is correct. This one is wrong. In this case, if this bond cleavaged, what will get the answer? Here H, here I. If this bond cleavaged, here H, here I, because oxygen side HL will attack. So for the first case, what is the answer? Methanol. Second case, what is the answer? First case, this one, methanol. This cleavage, what is the answer? Propanol. Which is correct in this case? Second one is correct. First one is wrong. How? How first one is wrong? Why second one is wrong? What is the matter? It's very simple. The point is, that's it. If the given ether has any side, either left or right, whatever, any side, tertiary carbon, anywhere tertiary carbon is there, it follows SN1 mechanism. Primary or secondary carbons usually follows SN2 mechanism. Okay, tertiary carbon follows SN1, primary, secondary follows SN2. Now see here, this carbon is a tertiary, this carbon is primary. I said any one carbon is tertiary. So here tertiary carbon is there now. So 100% first example mechanism is SN1. According to SN1, what is the main step is, SN1 means here intermediate is carbocation or not. You know, in this two, which carbocation is most stable? I'll write here normally. Tertiary carbocation is most stable or ethyl carbocation is most stable? Tertiary carbocation is most stable, na? Why? Hyperconjugations, most stable intermediates, more reactive. Tertiary is more reactive than primary. So 100% this carbocation is formed. So whenever this carbocation is formed, the negative part is attacked. That means what? I. And right side is what? Ethanol. Simple. Right? Iodide on left, alcohol on right. So only this one is correct answer, not this one. But if I go for second case, this is primary or maybe secondary also, it's not a matter. And this is also primary. But don't take tertiary. So both are primary here, or maybe one is primary, one is secondary, also not a problem. Then it follows SN2 mechanism, right? According to SN2, less crowded group easily react in SN2. So in this two, where less crowded, this one. So what is the nucleophile here? This is negative. Nucleophile is I minus. So I minus attack to where? At here only, na? This bond cleavage, right? So what will get the answer now? Propanol plus methyl iodide. So this one is correct, what I said. In this case, see here, phenyl group, oxygen having lone pair, this is involved in resonance or not? So this bond difficult to break, but RO bond easily break. Either it is primary or secondary or tertiary, it's not a matter. Anywhere, this bond only cleavage, left side is not possible. So here H and here I. That means left side is phenol is fixed product plus RI, methyl or propyl or isopropyl, tertiary, we have to check it. And what about hot conditions? Hot conditions very easy. This iodide is as usual, and whenever alcohol is there, react with Hi, H2O removed or not by heat, we'll get iodides. Here also same, iodide. That means in this case, two sides iodine you will get. It's not a matter. Mostly heat is there, no need to use either SN1 or SN2. Directly you can write iodides. Only the important case with cold. But in the previous sections, previous example, they gave sometimes hot, sometimes cold also. So we need to check whether it is a cold or hot condition and products properly. It's very, very important. Previous questions are there. And one more theory in this one, that is the cleavage of epoxide. I'll tell you briefly just. Epoxides. What is epoxide? We know. 3-membered ring with oxygen is called epoxide. First, I treated with H plus ion. What is the reaction? Here oxygen having lone pair, base, and here acid. So it gives like this. Very simple. Now, any one of the bond must be cleavage, either right or left, because O plus is unstable, na? But left side is more preferred. Why? Secondary carbocation, right? So if this bond shift, it becomes secondary carbocation. This bond shift, it becomes primary. Primary, secondary, which is more stable. Secondary. That's why left side cleavage takes place. And if I used any base or some negative ion, nucleophile attack on carbocation, we know here OH and here Nu. So finally nucleophile on left, OH on right. See the mechanism. First H plus attack, carbocation formed, then nucleophile is attacked, right? And if I used same for basic medium, now starting only some negative ion I used. Now here lone pairs are there, but lone pair negative charge having repulsions now. Then this carbon is partially positive, here also partially positive. But where partially positive charge is more here, because here donating group is there. Whenever the donating group is there, charge decreases, nucleophilic addition difficult. I said already, nucleophilic addition directly proportional to withdrawing groups and inversely proportional to donating groups. So this nucleophile attack at here in this bond shift, how you will get? See here OH, here nucleophile. Okay, directly contact. And finally we can add H plus from the water, nucleophile, and here OH. See the difference between earlier and this one, both are opposite. Okay, I'll show you with example. This is the last for ether chapter. This is the first one. Second one, how to solve the questions. Very simple. See here, this carbon is partially negative and here oxygen is positive, here also positive, right? So this C minus approaching here, only one methyl group is there, but here two methyl groups, more repulsion, so 100% it will attack at here. This bond will cleavaged. What is the answer now? Here CH3 attached and here O minus, and finally H plus from the water. So here OH methyl groups, like this you will get, correct? But in this case, first H plus is there, so H plus attack on this part. We know secondary and tertiary which is most stable carbocation, secondary. Now here see earlier right side, now left side cleavage takes place. OH and here positive charge. But what's the negative part here? CH3O minus H plus. Don't confuse, it's very important. Don't write as OH minus and R plus. That is not correct. RO minus H plus is correct. The cleavage always RO minus H plus, not R plus OH minus. Here negative part is not OH minus. Negative part is what? CH3O minus. So that CH3O minus attack it here. Here we get OCH3. Understand? Like this. Very easy. So this is about ether chapter. Also done. The last chapter we are discussing for today's class, that is phenols. I think so now you're understanding organic very easy, right? Yeah, don't feel like that. Okay, it's very difficult, so 100% you need to practice much. If they give question organic, they'll give dead easy questions or very hard questions. There is no moderate questions in organic. So easy or tough, only two part. Easy means okay, you can easily write, but tough questions time, only show your talent. Okay, fine. Now we are discussing phenol. The phenol, the first point, you know, the preparations usually you can study from the books, you can understand, not focusing on that part. The mainly chemical properties are very important for phenols. And by using benzene diazonium chloride, you know, that part you can easily understand. So chemical properties I am discussing. In the first one, if the phenol It acts as ortho-para director or meta director, and it's more reactive than benzene or less reactive than benzene, we need to know. See, the phenol, whenever reaction with any reagents, the first step is it must be lose H plus ion because it's a more acidic. O minus, H plus is removed. That means the phenol won't be react. Phenoxide ion react in the reactions. That's the first point. The second, when this phenoxide ion is involved, see the resonance. Double bond O minus. Again here, we know the resonating structures, right? Double bond O and here, and again resonance possible. Right, and finally it is phenoxide. So negative charge formed at ortho and para director, hence we can say this is ortho para directing. That means the electrophile always attack at ortho and para. If I used benzene and phenoxide ion, we have electrophile. See here the pi electrons approaching to the electrophile are not any pi bond, but here when it's formed as negative charge donates electrons. We know phenol donates pi electrons, benzene donates pi electrons, phenoxide ion donates negative charge. Which is more powerful donor? Negative charge. So what I want to tell you, the point is very simple point. The phenol is 100 times more reactive than benzene in electrophilic substitutions because of phenoxide ion formation. Whenever phenoxide ion is formed, the negative charge is formed at ortho and para, they are easily accept the electrophile. So phenol required some reagents to create electrophile, but phenol no need any reagents. Directly if you add some reagent, directly it can react. I'll show you with example, you get more clarity. So what I want to tell you, the point based on this, only one point, phenols are more reactive than benzene. See here, I'll show you. If I used phenol, the first one with dilute HNO3. See, the benzene won't react with the dilute HNO3 because nitration, if you want to prepare nitrobenzene from benzene, we are adding nitration mixture. What is nitration mixture? HNO3 plus H2SO4, right? We are using HNO3 plus H2SO4 and both react. One acts as acid, H2SO4 acts as acid, HNO3 acts as base. So finally we will get NO2 plus, electrophile NO2 plus. That NO2 plus substituted on benzene and it gives nitrobenzene, right? But here we don't want any sulfuric acid. The reason I said earlier, benzene is more reactive, phenol is more reactive than benzene. So benzene required some reagent to give electrophile, but here no need any further reagent. Directly react with the direct reagent like nitric acid, directly react. So here phenoxide ion negative charge is there, that negative part attack on NO2, it pull the NO2 from nitric acid itself. So the finally we will get two products. One is OH with NO2, the second one ortho directing and para. I said already phenoxide ion phenol is more reactive at ortho and para with electrophilic substitution. Now in this two, which is major? Usually this is major because of no repulsions, but in this case this is major because of hydrogen bonding. Due to hydrogen bond formation, orthonitrophenol is more reactive than para-nitrophenol. Okay, and SDT also same, para is more acidic than ortho. So in Jingosi already we discussed SDT. But usually ortho having repulsions, for example here some chlorine or some A group is there, some X group is there, then repulsions are there, so this is unstable. More repulsion, less repulsions, more stable. Then para usually major than ortho except hydrogen bond cases. If I used concentrated HNO3, I told you already the phenol is more reactive and nitric acid here concentrated, that means both are reactive. Once both are highly concentrated, then what happened? So reaction is very fastly and effectively takes place. So we will get all NO2 groups at ortho and para positions because of both are highly reactive. Hence it gives picric acid. And if I used concentrated sulfuric acid, don't take dilute, because of dilute means it absorbs water, dehydrating agent. The strength is very weak. So we are taking usually concentrated sulfuric acid for this one, and it gives, it's a bulky group, can't exist with the 3 positions. That's why it forms as SO3H and SO3H. Usually at room temperature this is measured, at 100 degrees Celsius this is measured, and here also same, at room temperature this is measured, at 100 degrees above temperature this one is measured. Why? At high temperature, see, generally usually here hydrogen bonds are there. High temperature hydrogen bonds are cleavage, that means no hydrogen bond. If there is no hydrogen bond, which is major product? Para only, na? That's why high temperature is para, low temperature is ortho. But if there is no hydrogen bond, I'll show you, like example, Cl2 with FeCl3. In this case we will get Cl at here and at here, right? But see, this chlorine won't be react, no hydrogen bonding here. Then in this which is measured at low temperature, high temperature, whatever the temperature, this one is measured because no repulsions. And if I used bromine water, Br2 with H2O, they produce Br plus. They produce Br plus. We know HBr removed and HOBr, Br plus. Concentrated, this is also more reactive. Both are highly reactive. Then all bromines substituted at ortho and para. So it gives white precipitate, and we are using bromine water test for phenol. We are using test for phenol. Next, HCl plus HCl and H3O plus anhydrous ZnCl2, like these reagents we are using, these all are used for Gattermann's aldehyde reaction. We will get aldehyde groups, and this is measured because of hydrogen bonding. And one more, like CO plus HCl anhydrous ZnCl2 also gives same reaction. So these all are normally from the benzene chapter model. So we will get electrophiles and the same pattern. Go through it. Okay, these are the main chemical properties of phenol. And 2 more phenol properties. In their first one, Reamer-Tiemann reaction. Reamer-Tiemann reaction. What is Reamer-Tiemann reaction? See, we know the normal reaction, base reaction, it's not that much important. Is react with chloroform plus alcoholic KOH. These two are combined, it gives CCl2. Whenever CCl2 is there, what happens? I'll show you. And finally it gives aldehyde like this. This is Reamer-Tiemann reaction. What the exact mechanism? I said first phenol converted into phenoxide ion in the medium. Then this phenoxide ion react with the dichlorocarbene. It forms as like this. Ortho and para directing, but ortho is measured because of hydrogen bonding. I said already, hydrogen bond is there, ortho is measured. Otherwise para also possible, no doubt at all. Now here double bond O, and here bond Cl, Cl. See, it gain electrons, get negative charge, and double bond O like this, right? But see, this is the key point. Now, earlier H plus removed from the phenol, right? So we are adding that H plus. So this H plus attack on where? This H plus attack to C minus or OH here. See here, oxygen having lone pair, and here C minus. So O and C, which is more powerful donor? Obviously C only. So this first H plus attack on this C. So whatever the H is removed from here, that H will attack at here. See, if they give OD for example, CD we can write, no doubt at all. Then already they gave KOH solution, K plus Cl minus removed and OH groups attack at here. H2O removed. Right? It is involved in tautomerism because of hydrogen. This is the product, right? So whatever the hydrogen present on the carbon, that hydrogen shifted finally to the phenol. So these hydrogens are not same. These hydrogens are not same. Okay. So by using the mechanism, you will get idea. Just check it. This is important mechanism. I'll give you one more important application here. Instead of chloroform, if I take CCl4, carbon tetrachloride, we will get benzoic acid, that means salicylic acid. This is salicylaldehyde. We will get salicylic acid. Instead of aldehyde group, COH you will get if you take pyrrole, carbon tetrachloride, CCl4. Okay. Now see this reaction. If I took pyrrole, reacts with CHCl3 plus alcoholic KOH. We know these two combined, it gives always dichlorocarbon. The final answer, we will get two answers. The first one, this is first one, it's a major product because of hydrogen bonding. This is major. The second one, either here also can possible, I am not discussing that part. And the second also major product, two major products here. In these two, which is major? It's the meaningless question. So both are possible. Okay. So this one and also 3-chloropyridine. How 3-chloropyridine formed and why here only reaction takes place? We'll see. Before that, first we need to know the resonating structures of pyridine. Oxygen, nitrogen having lone pair. This bond shift and this bond shift. Here double bond. Here N plus, right? Again, this bond shift, this bond shift. And again, like this. Okay, again see, focus more. The last part. This is the resonating structures of pyrrole, right? So where we got the negative charges, check it. First negative charge at here, second negative charge, third, fourth. That means we are getting at here, 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 here. The four places we will get negative charge. So whenever the CCl2 attack here, either negative charge, these two are identical, these two are also identical. I am taking either here or here. So CCl2 attack first on this carbon, like here, or maybe at here, like same previous CCl2 attacked then rearranged, and finally we got aldehyde or not. The same thing happened here. Negative charge formed and CCl2 become aldehyde. And here also we will get one more aldehyde. But in this two, which is measured at second position because of hydrogen bonding. Clear? So the first part is clear. Why it is formed and all. Why? Because of negative charge formed, the CCl2 attack followed by hydrolysis, we will get aldehyde. But how pyridine is formed? That is also important. We will discuss. This is another way. Pyrrole treated with CCl2. The one important application for carbene is it may involve in insertion reactions. What is that insertion? See, here pi bond is there, no? This pi bond donates to this carbon because it's electron deficient. Whenever it donates electrons, again lone pair is there, it will go here. Like, careful. Okay, this bond as usual, and you'll get a new 3-membered ring. No loss, no gain. Just simple coupling, like for 3-membered, 2 double bond, and this will form as 4-membered ring, like this. Now, but 3-membered ring unstable, we know this bond donates, and Cl minus is the leaving group, good leaving group. So Cl minus is easily removed. Then what happens? See, I'm taking, it's a better for understanding purpose, I'm taking numbering. Okay, 1, 2, 3, 4, 5, 6. 1,2 bond formed and 2,6 cleavage, right? That means Cl writing. I'll get the number. 1, 2, 3, 4, 6. See here. 4, 5 having double bond. 3 has nitrogen, right? And 1, 2 new double bond is formed. And chlorinate 1. 6th one have positive charge because it lose bond. Check carefully. That is important. 1, 2 new bond formed. Cl, 1 Cl removed. Now only 1 Cl is there at first carbon. 6th one has positive charge because it loses electrons. Now the last step, this bond shift, either left or right, it's not a matter. This bond shift and the proton removed. Earlier Cl removed, now proton removed as HCl. We got finally 3-chloropyridine. 3-chloropyridine is formed. Understand? So this way we can do it. And next one, coal-base reaction by using phenol. See, the two reagents I want to tell you. The first one is carbon dioxide with NaOH, carbon dioxide with KOH. Very important. The NaOH gives salicylic acid ortho position, because the same thing, this bond shift and COO is there, na? COO, that H shifted here and it becomes the carboxylic acid. The mechanism same as previous. Instead of CCl2, just take this one and mechanism easy. You can easily get it. But here sodium ion is there. See, the sodium is small size, so ortho 5-membered 6-membered ring is formed, and this is more stable with hydrogen bonding followed after that. But if I used potassium, then the final answer is phenol as usual, and para position is the measure. Here this is the measure, and in this case measure, because of potassium hydroxide. Whenever you used potassium hydroxide, the potassium is more crowded atom, so difficult to form ring at ortho position. So the para repulsions are less, so it is more preferred. So sodium small, so no repulsions, hydrogen bond easily formed. KOH repulsions are more, hydrogen bond is not formed easily. That's why here para is measured, here ortho is measured. And one more reaction, so last reaction for phenol, test for phenol. So already I gave earlier test for phenol, that is bromine water test. If I used bromine water plus phenol, it gives 2,4,6 tribromophenol. The color is white precipitate, I said. That's the first test. The second one is neutral FeCl3. If I used neutral FeCl3, if I used, then it gives violet colored complex with the phenols only, or stable enols, violet colored complex with this one. That's the second test. And the third one is Lieberman nitroso test. It's the last test for phenol. Okay, I'll give you. It's very simple. First we need to take phenol. It is treated with HNO2, not 3. 3 gives NO2, right? HNO3 gives NO2. HNO2 gives then what? NO. And the measure is here OH at here, because it is more involved in tautomeric form. That's a para nitroso. NO group is called nitroso compound. Nitroso. SO. Nitroso. Now again this compound reacts with another mole of phenol. Okay, now what happened here? See, this bond shift, this bond shift, this bond shift, this bond shift, and H attack here, and OH and H formed as H2O. Enol form I'm writing. See, I'll show you. This for compound I'm writing. Double bond O, bond, double bond, and OH. This OH and H removed. That's why instead of that I'm writing phenol. That OH group is there now. So OH, see here, that OH and H removed, and this form is at here, para position. This is called coupling reactions. And by using sodium hydroxide, actually this color is red colored complex. Whenever you use sodium hydroxide, it forms like this. It's a dyes. Okay, red become blue color dye. This is red color dyes. So first we will get nothing, very simple. Take phenol and add nitrous acid, and itself reaction takes, excess of phenol we need, itself reaction takes place, and it gives finally red color dye. And for more for other confirmation, add sodium hydroxide solution concentrated, then immediately it become blue color. So based on that, the confirmation is what? The given compound is phenol. This is called Lieberman's nitroso test. So this part I want to tell you, alcohols, phenols and ethers. Hopefully you understand, and the remaining we'll discuss next class, remaining chapters. So practice more questions. Okay, don't waste your time. I know morning to evening full time is in our hand, so you're bored with studies, but you have to study. It's a good chance for you. Don't miss it. Hopefully you'll get good ranks. Thank you. Bye.